Hi, I'm Jairaj. My project for wireless communication is wireless link setup and analysis in IEEE 802.15.4. In this, I'll be setting up a physical link between two embedded RF modules, and I'll be uh, discussing the step-by-step procedures in establishing a wireless link. Also, there will be a software, X-CTU software, that will be used for configuring the modules as well as setting up the link, as well as useful for taking useful physical data will be explained in detail. After the wireless link is set up, I'll be conducting some field tests like received signal strength measurement and received packet ratio. This data will help us analyze uh, the range as well as the link quality of the setup link. Uh, Now we'll go ahead and see the PPT. Where is it? Yeah. Okay. First of all, we'll go through the background. Uh, the modules used 2.4 gigahertz in the frequency, and the physical and MAC layers support 802.15.4 radio, whereas the high layer is a Zigbee protocol. These modules are low in data rate, power, cost, and bandwidth. They are quite popular. Why? Because they are small, uh, efficient, and mostly solve the purpose where low data rate, power, cost, bandwidth is required, like home automation or wireless mesh networks, sensor networks. Also, act, uh, they can form several topologies like point-to-point, star, mesh, cluster tree are all supported by these modules. Also, the functionality they can support is end node, router, coordinator, all three functionalities. So they are quite popular, and we'll be using these modules. Second is the setup. So what hardware we are going to use is I'll be using BG's XBee Series 2 module, ZB24WID, that's its serial number. Uh, and as these modules are serial, that is the data they give up is serial, I'll be using a SparkFun XBee adapter for for interfacing into the computer. It's a serial to USB and vice versa converter. Uh, this this DGXB Series 2 module uh, will be covered up later. I'll show you in detail what's it. Uh, After my hardware selection is done, I'll be explaining the hardware configuration. For this, I'll be using X-CTU software and addressing schemes. Also, the coding required for enabling or configuring these modules will be AT command mode programming. That also I'll explain in detail later. Then after my link is set up and my modules are configured and the link is set up, I'll be doing some experimentation like setting a wireless chat link between two computers to test the link, and then once that's successful, I'll be conducting a range test and a received packet ratio measurement in different field environments, outdoor, indoor. I'll explain, I'll plot those results, and I'll explain from the observations what I conclude. So this is the embedded RF module, that is DG's XBee ZB24WIT module. As you can see, it's serial pins. Uh, it has a chip antenna. Sorry, not chip antenna. It's a whip monopole antenna. Uh, it's a complete package. It has a processor, uh, AMBER processor for flash programming. As I told before, the physical layer and MAC layer is IEEE 802.15.4, whereas the high level protocols have Zigbee configured Zigbee routing protocol. Okay, and this is the serial to USB to serial register that I'll be using for connecting this module to my laptop. This, so I'll be using this. This is a FTDI's serial to USB, USB serial convert chip. And as you can see, the pins are given for interfacing this module directly on it. So the module will be seated on this like this, and this module I will be using a pair of this. And as you can see my setup, they are interfaced to laptops, and this forms one of my communicating node, and this forms my another communicating node. So a minimum of two are required for setting a wireless link. And yep, my link is set up. Now all we need to do is configure these modules, so which will explain later. See, this is the how I configure the modules. After those two modules are connected to my laptop USB port, you open up X-CTU software, you select the COM ports, you set up the baud rate, hardware, data bits, SAT, stop bits, that is the communication settings that require to communicate from the computer to the module. After you are, after you have selected the various parameters of communication, you push the test or query button, and this is what you see. This shows that the communication with the modem is okay. That is, it is able to communicate with the interfaced embedded RF module. It shows the modem type, the firmware version that it has been loaded with, and the serial number of that module. After those modules are connected, for my wireless link setup, I'll configure one of my embedded RF modules as a coordinator, whereas the another as a router. So in the modem configuration, I'll show you X-CTU software. This is X-CTU software, the static PC settings that we talked about earlier. This is the modem configuration, where you can select the modem type. Once you are done, as our module is XBee24 Zigbee, you can select the function type and device coordinator, various the versions, and this is what you get. You can also read from the module what all data, what all firmware is already loaded in the module, whereas you can write a new function set inside the module as well. So I'll be connecting one of the module and writing function set coordinator in one of the module, whereas in another I'll be using a router firmware. Once that is done, I'll open up a terminal section. This is the terminal section. I have not connected the module right now, so you won't be able to see it. This here I want to configure the addressing of those modules, because as you know, like coordinator will be communicating with the router, so coordinator must have the address of the router as its destination address, whereas the router must have the address of the coordinator as its destination address. So this is an ET command mode. These are the various syntax used to configure the module, the address of the module. This is the code that I have written in my module. This is for the device configured as coordinator, the ET command mode. This is used for getting into the command mode, because normally it is in the transparent mode, that is in the communication mode. Then this AT command just checks whether you are still the communication with the Zigbee module is on. Then this setups the power level of your transmitter module. This reads the node, which node is it. This AT-ID assigns a PAN ID, and for setting up a wireless link, you have to assign a same PAN ID to both the devices, so they are within a network. And this AT-ID with the carriage return reads the PAN ID, so you can confirm whether the same ID has been written to the device. This ATSL gives the source, that is the module that you are using, address, whereas ATDL, you can write the address of this is the address of the router module that I have written inside the coordinator. And this final ATWR writes the configuration changes to the module, and ATCN leaves the ET command mode. So same way we have done the coding for the router, except that the destination address would be that of the coordinator. So once we're done with this, uh, we'll set up a chat link where you open up a terminal section of both those in both the computers which have that module connected. And once you start typing in one of the terminals, the same data will be reflected in the second computer, which is the second communicating node. Here you will see the number of bytes that is received, and the COM port used, the data baud rate, the number of bits, the flow, and all. So once the chat link has been set up, uh, okay, once the chat link has been set up, we are sure like whether those two links, whether the wireless link has been connected, and once it has been done, we'll move on to our performance analysis. We'll be conducting a range test and a received packet ratio measurement. This is the house plan of my apartment. These are the exterior walls. This is the lobby. These are the interior walls. These are the different rooms. Uh, I've kept a coordinator node stationary in the center room, whereas I'll be conducting uh, receive signal strength measurement in different rooms like A, B, C, and D. A and D are at same distance from M. B and C are at same distance from M, and in the lobby also. So this shows that the different positions router node will take. Uh, as you can see, L is the lobby, A, B, C, D are the test rooms, M is the main room. Sorry for that. Uh, the distance I have measured is 30 feet for room A and D, and whereas in B and C is 23 feet from the main node, and router in the lobby will be at 168 feet from the coordinator node. Okay, this this is the uh, received signal strength measured versus time in room A at a stationary point. As you can see that there's quite a bit of fluctuations in the received signal strength, even if we are stationary at the same distance from the main coordinator node. We experience these fluctuations with time. Room B shows similar random fluctuations in received signal strength. The received packet ratio is 100% though. Here too it's 100% though. In room C it's again different. As you remember, like B and C were at the same distance, even though the received signal strength acts differently, the curves are different, the fluctuations are random. In room D, again there's a different fluctuating curve. Again the received packet ratio is 100%, that means the quality is good. This test have been conducted for uh, 35 to 35-40 results data. So what's the observation I made? The observation is that for same distance there was different received signal strength measured. This fluctuations in RSSI with time at fixed location. What can be the causes of this? It's multipath, obviously. Also interference, as there is Wi-Fi, there's obstacles, there's walls, location, you can say. Those kind of these two contribute to the random fluctuations. This is the, as you can remember, my lobby experiment. It was like 128 feet away from my main coordinator node. This is the received signal strength I measured. Here I lost my signal, so the received packet ratio dropped to 34%. As you can see, the Zigbee module cannot uh, determine a signal if it's below -0.04 dBm. So you can see, even if I'm at a same distance, I'm not moving, still with time the signal varies drastically, so drastically. Now I did a second experiment. Here it was with respect to distance, the signal strength measured. For this, it was an indoor lobby we saw earlier, but in this experiment, the main coordinator node is at line of sight with the router node. The coordinator node has been kept stationary in the lobby, and we'll take the laptop that has the router mode, and we'll keep on moving further away from the coordinator node. So at distance 0 is like at the same distance where the coordinator node is, and we'll keep on moving at fixed time uh, in an interval of 3 feet, and this is over the distance of 140 feet that I measured. So as you can see, the signal again fluctuates in time, so it's not dependent only on the distance. Yes, signal attenuates with distance, but it's not like a linear curve. As you can see, it drops quite below, quite below at 20 feet, but it jumps high again at 40 feet. So the signal strength at 40 and 10, it seems to be the same. So this is, as you can see clearly, it's due to multipath feeding. It's additive, destructive. Also due to interference, we cannot predict exactly what's the reason, but this is what we can guess. It's like due to multipath interference, as it's indoor, so signal strength can increase drastically as well as decrease drastically, depending on whether the signals are additive or destructive. But averagely, on an average, it decreases. Signal strength decreases with distance. So you can say it follows some path loss model, and this is the same experiment conducted. Oh, sorry, it should be outdoor lobby. Sorry for the mistake. I forgot it completely. It should be outdoor line of sight. It was conducted in a free space outdoor. As you can see, the distance I'm conducted this experiment was 350 feet, and the received signal strength that I measured. Again, like on an average, the signal decreases as distance increases, but still you can see the random fluctuations in the signal, but they are not as random as the indoor model. Here I lost signal a couple of times, so the receive packet ratio drops. Drop is pretty bad, it's 23%. From this experiment, you can make out like uh, the received signal strength is dependent on the path loss, attenuation due to path loss, as well as multipath and interferences or obstacles in its course. So the observations, we measured a fluctuating received signal strength. Uh, the signal decreases with distance obviously, but it's not a linear curve. The received signal strength influences ratio, received packet ratio. Uh, yeah, it influences very low RSSI, would definitely result in drop packets. But obviously, the reverse is not true. Like the received packets ratio uh, doesn't entirely depend on the RSSI, as you can see from the indoor experiments that we considered earlier. I'll show you. To be in, yeah. Even if the signal is pretty low, you are able to still receive a packet ratio of 100%. So you can say like RSSI determines the received packet ratio, but it's not dependent entirely on the received signal. Many different uh, causes like interference and obstacles are also responsible for packet ratio loss, even if the signal strength is high. These are the causes you can see. Causes I found out to be the multipath, destructive, or additive. The interference, again, the interference issue. Path loss, obviously. Uh, for an ideal condition, the path loss determines the receipt signal strength, but combined with multipath and interference gives the graph that we previously obtained. The conclusion, yeah, wireless link setup was successful, smoothly done. I explained all the parameters required for the setup. Very important test that X-CTU offers. I forgot to show you like where is the range test in X-CTU. Here is the range test, and this is a snapshot of the range test, how it will look. This is the received packet. It's 32 byte. The number of packets, good, bad, drop packets, received packets. The received signal strength is minus 40 dBm, and the lowest is minus 104 dBm. So this shows you the received signal strength. Uh, I opened this terminal on both the laptops, and one was fixed, stationary, transmitting a fixed number of bytes, whereas the router node that I had in my hand while conducting the field test was receiving these packets, and I was constantly monitoring the received signal strength and the number of packets received. So this percentage gives the received packet ratio. So back to the okay. So what are the observations? The observations that I summed up earlier was my conclusion. Future work, yes, a lot of future work to be done. It's like the field data that I obtained can be used to estimate channel in the feeding model in the environment using appropriate algorithm. From the data we got some path loss, uh, signal strength plots. From then, from that we can use it to estimate the channel in which we are conducting the experiment. Uh, yeah, after a link is set up, the second step would be setting up a wireless network, which will be obviously using more than 3 of such nodes. And yeah, that's it for my project. I think you like it. I hope you like it. Sorry, I hope you like it, and thank you for your time. Bye bye.